Hi, I'm Inslee, and I'm an applications engineer at Hanna Instruments. Today I would like to demonstrate how temperature can affect electrolytic conductivity. Conductivity is the ability of a substance to carry an electrical current across a defined distance and is measured in Siemens per centimeter. Electrolytic conductivity is the conductivity of a solution in which the transport of an electrical current relies on the presence of ions. Ionic mobility, or how well the ions move in solution, depends on the concentration and the size of the ions, as well as the temperature of the solution, among other things. As the temperature increases, ionic mobility increases, and this results in an increase in the apparent conductivity. As the temperature decreases, ionic mobility decreases, and this results in a decrease in the apparent conductivity. Almost all standards account for calibration to occur at 25 degrees Celsius. Therefore, compensation must be made for any measurements made at temperatures other than 25 degrees Celsius, unless the user is attempting to indicate the actual conductivity, or the conductivity of a solution without the temperature compensation. Temperature compensation is achieved with a linear temperature coefficient that uses percent change per degree Celsius for units. Several common substances have known coefficient values that have been published and can be manually entered when taking measurements. Hanna meters use automatic, manual, and no temperature compensation. For a fixed temperature coefficient, the default value is 1.9% per degree Celsius. This means that for every degree away from 25 degrees Celsius, the reading is adjusted by 1.9%. This value is based off of the conductivity experienced by a standard 0.01 molar potassium chloride solution. It is recommended that the temperature of each sample be recorded, as well as the conductivity of the sample at 25 degrees Celsius. To demonstrate the effect of temperature on electrolytic conductivity, we will be measuring the conductivity of two solutions, a cold saltwater solution and a hot saltwater solution. Each solution was prepared from a stock saltwater solution, so it should have the same concentration of salt. To aid in my demonstration, I will be using the Hanna Instruments HI 3512 benchtop meter. This meter has automatic and manual temperature compensation, as well as the ability to automatically measure in the range appropriate for the sample from 0 to 400 millisiemens per centimeter. So let's measure the conductivity of a cold sample of salt water without temperature compensation. As you can see, at 6.3 degrees Celsius, the conductivity is 1.472 millisiemens per centimeter. Now let's measure the conductivity of a hot sample of salt water without compensating for the high temperature. At 42.1 degrees Celsius, the conductivity has increased to 3.380 millisiemens per centimeter. Next, we're going to measure the conductivity of the cold sample of salt water with automatic temperature compensation turned on. With the compensation disabled, the conductivity was 1.472 millisiemens per centimeter. Now it's 2.289 millisiemens per centimeter. Finally, we'll measure the conductivity of the hot sample of salt water with the temperature compensation enabled. Last time we measured the sample, it was 3.380 millisiemens per centimeter. Now it's 2.286 millisiemens per centimeter. Let's review what we learned today. First, we demonstrated actual conductivity by showing that a cold water sample has a lower conductivity than a hot water sample. This is because as temperature decreases, ionic mobility decreases, and this results in a decrease in the conductivity. The opposite is true for increasing temperature. Next, we showed apparent conductivities by showing the ability of the HI 3512 to automatically compensate for variations in temperature of different samples. I hope that these demonstrations helped with your understanding of how temperature can affect electrolytic conductivity. If you have any questions in the future, please feel free to contact your local Hanna office at www.hannainst.com. Thank you.